Pick up anything near you right now. It could be a pen, a cup of coffee, your phone, or simply look at your own hand. It looks solid, doesn't it? It feels like a real, concrete thing made of matter. For centuries, that's exactly what we believed. We believed that everything in the universe was made of tiny particles called atoms, and that these atoms were like invisible little balls, forming everything that exists. But modern physics discovered something profoundly strange. That picture is completely wrong. In reality, what you are holding right now, and even your own body, is not made of small, solid things the way we imagine. What truly exists is something much stranger, much deeper, and also much more fascinating. You are not made of things. You are made of fields. Before that sounds too abstract, it's worth slowing down and understanding what this means. Because once you truly grasp this idea, the way you see the universe changes completely. To begin, think about something simple that all of us have seen countless times. An ocean wave. Imagine you're standing on the beach watching the sea. Waves move toward the shore one after another, creating that hypnotic motion of water rising and falling. Now consider a curious question. When a wave travels across the ocean, does the water itself move all the way from the middle of the sea to the beach? The answer is no. If you observe carefully, you'll notice that the water doesn't travel very far. Each small portion of water simply moves up and down. What actually moves is the pattern of the wave. The wave is not a thing. It is a movement that occurs within the water. The water is the medium, and the wave is just a disturbance that propagates through it. Keep that idea in mind for a moment, because it is the key to understanding something very deep about reality. For a long time, we believed that the universe was made of tiny, indivisible particles. This idea goes all the way back to ancient Greece. Philosophers imagined that if you took any object and kept cutting it in half repeatedly, eventually you would reach a point where it could no longer be divided. This smallest unit was called an atom, which literally means indivisible. For thousands of years, this idea seemed reasonable. The world appeared to be made of small, solid things that simply combined to form larger objects. But at the end of the 19th century, evidence began to appear that atoms were not so simple after all. In 1897, the physicist J.J. Thomson discovered something unexpected inside the atom, the electron. It was an extremely small particle with electric charge, far smaller than any known atom. This changed everything. Suddenly we realized that the atom was not indivisible. It had internal structure. A few years later, another scientist named Ernest Rutherford discovered that almost all of the atom's mass was concentrated in a tiny nucleus at its center. From this came a famous image, the atom as a miniature solar system, with the nucleus at the center and electrons orbiting around it like planets. It was an elegant idea, simple and easy to visualize. But there was a huge problem. If electrons were really tiny charged particles orbiting the nucleus, they should constantly lose energy. According to the laws of electromagnetism, an accelerating electric charge always emits radiation. That means the electron should quickly lose energy, spiral inward, and crash into the nucleus. If that were true, every atom in the universe would collapse almost instantly. All matter would cease to exist. You wouldn't be here. I wouldn't be here. Nothing would be here. The simple fact that the universe continues to exist was proof that something in that picture was deeply wrong. That's when one of the strangest revolutions in the history of science began: quantum mechanics. In the early 20th century, physicists like Werner Heisenberg and Erwin Schrödinger started developing a new theory to explain the behavior of electrons. And what they discovered was extremely counterintuitive. An electron does not behave like a tiny ball. It behaves like a wave of probability. Instead of occupying a specific point in space, the electron is described by something called a wave function. This function doesn't tell us exactly where the electron is. It only tells us the probability of finding it in a particular place when we make a measurement. In other words, before it is observed, the electron is not located at a single point. It is spread out. In a sense, it exists in several places at once. That was already strange enough to leave the scientists themselves puzzled. Yet even then, there was still a hidden assumption in the theory. The idea that particles were still fundamental entities of reality. Maybe they weren't tiny classical balls, but they were still things. Then an even deeper idea emerged, one that would completely transform our understanding of the universe. This idea is called quantum field theory. According to it, particles are not things. Particles are events. To understand this, we must completely abandon the traditional image of little balls traveling through space. Instead, imagine that the entire universe is filled with invisible entities called fields. A field is simply something that has a value at every point in space. The temperature in a room, for example, can be thought of as a field. At every point in the room, there is a specific temperature. It might be slightly warmer near the window and a bit cooler near the door. Now imagine that the entire universe is filled with different fundamental fields. There is an electron field. There is a quark field. There is an electromagnetic field. In fact, there is a field for every type of fundamental particle we know. These fields don't appear only in certain places. They exist everywhere. They extend throughout all of space in every direction, without exception. They were here before the first stars formed. They are still here now, and they will remain even when everything we know eventually disappears. These fields are the invisible fabric of reality. And here is the most surprising part of all. What we call a particle is simply a vibration in one of these fields. An electron is not an object. An electron is a small vibration in the electron field. A photon, the particle of light, is a vibration in the electromagnetic field. A quark is a vibration in a quark field. Just as a wave is simply a movement occurring in water, a particle is a movement occurring in a quantum field. When the field vibrates in a certain way, we detect that vibration as a particle. When the vibration disappears, the particle disappears, but the field remains. It was always there and always will be. This completely changes how we see the universe. In the old picture of physics, there was empty space with particles moving through it. Space was the stage, and particles were the actors. In the new picture, fields are both the stage and the actors. There are no tiny solid things traveling through emptiness. There are only fields vibrating. Everything we call matter, energy, particles, and forces are simply different patterns of those vibrations. Now think again about your hand. It appears solid. It seems to be made of matter. But at the deepest level of reality, it is just an incredibly complex pattern of vibrations occurring simultaneously in many quantum fields. A very stable pattern, a very organized pattern, but still a pattern. You are not made of solid little things. You are made of movements. You are made of processes. You are made of vibrations within the fundamental fabric of the universe. What's even more remarkable is that these vibrations follow extremely simple rules. A few relatively compact equations describe how these fields interact with one another. From those interactions emerge atoms. From atoms come molecules. From molecules come cells. From cells come organisms. And eventually something emerges that can look at the universe and ask what it is made of. That something is us. This may be one of the most extraordinary ideas science has ever revealed. At the deepest level of reality, the universe is not made of things. It is made of activities, of motion, of continuous vibrations and fields that fill all of space. And somehow, at some point in cosmic history, some of those vibrations organize themselves into extremely complex structures, complex enough to become conscious, complex enough to ask questions, complex enough to try to understand themselves. But this leads to an even more fascinating question. If everything is made of fields, if particles are just vibrations, and if these fields exist everywhere in the universe, then why are all particles of the same type exactly identical? Why does every electron in the universe have exactly the same mass, the same charge, and the same properties? That question led physicists to an even deeper discovery about the nature of reality. And that is exactly what we will explore next. When physicists began to accept the idea that particles are actually vibrations in fields that fill the universe, a new question immediately appeared. If each particle is just an excitation in a field, then why are all particles of the same type absolutely identical? Why does every electron in the universe have exactly the same mass, the same electric charge, and the same quantum properties? It doesn't matter where the electron is. Inside a distant star billions of light years away, in a laboratory on Earth, or inside your own body. An electron is always exactly the same as any other electron. In the classical world, this would be extremely strange. Imagine a factory producing billions of tiny metal balls. Even with the best technology, there would always be small differences. Some would be slightly heavier, some a bit smaller, some with microscopic imperfections. The nature of physical manufacturing inevitably introduces variation. But in the quantum universe, this doesn't happen. Fundamental particles are perfectly identical. There is no electron that is slightly different. There is no electron that is older or younger. They are all exactly the same. The reason becomes clear when we return to the idea of fields. If an electron were a separate object wandering through space, it would make sense to expect small differences between them. But if all electrons are simply vibrations of the same fundamental field, then they are all manifestations of the same underlying phenomenon. It's like waves in the ocean. No matter how many waves there are or where they appear, they are all made of the same water and obey the same physical laws. The wave is not an independent entity separate from the water. It is simply a pattern that emerges within it. In the same way, every electron is a vibration in the same electron field that permeates the entire universe. Each time that field vibrates in a particular way, we detect it as an electron. And because the vibration always follows the same fundamental equations of physics, every electron ends up having exactly the same properties. In other words, there aren't billions of different electrons scattered across the universe. There is only a single electron field, and every electron we observe is simply a tiny ripple within it. This idea leads to an even deeper conclusion. The entire universe is composed of a small set of fundamental fields that extend throughout all of space. These fields exist everywhere at the same time, even in what we call the vacuum, where there apparently seems to be nothing. The fields are still present. The vacuum is not truly empty. It is simply a state in which these fields are at their lowest possible energy level. But even in this seemingly calm state, something surprising happens. According to quantum mechanics, fields can never remain completely still. There are always tiny, unavoidable fluctuations known as quantum fluctuations. This means that even in the most absolute vacuum we can imagine, the fields continue to vibrate slightly. Small virtual particles constantly appear and disappear, emerging for a brief moment and then vanishing again. This phenomenon has actually been observed experimentally. One of the most famous examples is the Casimir effect. When two extremely close metal plates are placed in a vacuum, the quantum fluctuations of the fields create a tiny force that pushes the plates toward each other. This force literally arises from the vibrations of the vacuum itself. What we call empty space is not truly empty. It is an invisible ocean of quantum fields constantly oscillating. This realization radically changes our understanding of reality. Instead of a universe made of solid objects separated by empty space, we begin to see the cosmos as a continuous fabric of interacting fields. Particles appear when these fields vibrate. Forces arise when these fields interact. The entire structure of the universe emerges from these fundamental dynamics. But the story doesn't end there. These fields do not merely exist side by side. They also interact with one another in very specific ways. The electron field, for example, interacts with the electromagnetic field. This interaction allows electrons to emit and absorb light. When an electron changes its state within an atom, it can release energy in the form of a photon, which is nothing more than a vibration in the electromagnetic field. These interactions are described by a mathematical framework known as quantum field theory. This theory is currently the most precise framework science has ever created to describe reality. Its predictions have been experimentally tested with astonishing precision. In some cases, theoretical predictions match experimental measurements to as many as 12 decimal places. That level of agreement is almost unbelievable when we consider the complexity of the universe we are trying to describe. One of the most famous applications of this theory is the Standard Model of Particle Physics. This model describes all the known fundamental fields and the particles that emerge from their vibrations. Within this framework, we find particles such as electrons, quarks, neutrinos, and photons, as well as the particles responsible for the fundamental forces of nature. Quarks, for example, are vibrations in fields that form protons and neutrons. These protons and neutrons combine to form the nuclei of atoms. Electrons exist around these nuclei, forming complete atoms. Those atoms then combine into molecules, and molecules make up everything we see in the world around us. When we look at a tree, a mountain, or a person, we are actually observing an incredibly complex structure of coordinated vibrations in many different quantum fields. It is as if the universe were a gigantic cosmic symphony, where each field is an instrument and each particle is a note played within the music. But there is still a curious detail in this story. If the universe is composed of all these fundamental fields, then where did they come from? Why do these fields exist at all? And why do they have exactly the properties they have? These questions still do not have definitive answers. They remain among the greatest mysteries of modern physics. Some scientists believe that all fundamental fields may be manifestations of something even deeper, perhaps a single fundamental field that appears in different forms. Others explore theories such as string theory, which suggests that particles might be vibrations of tiny microscopic strings in extra dimensions of space. Regardless of the final theory, one thing already seems clear. What we call matter is not really a collection of solid objects. It is a dynamic manifestation of fields that permeate the entire universe. The world we perceive as stable and solid is actually the result of highly organized patterns of vibration. This means that at the deepest level, reality may be much more like music than like matter. It is a system of rhythms, frequencies, and interactions that extend across the cosmos. And perhaps the most astonishing idea of all is this: every atom in your body, every electron in your cells, and every particle in your brain is simply a small vibration in those same universal fields. The same fields that exist in the most distant stars of the galaxy, and the same fields that existed billions of years before the Earth was formed. In a sense, this means you are not merely inside the universe. You are literally an expression of the universe itself in motion. Realizing this opens the door to an even deeper question. If all reality is made of invisible fields that permeate everything, what exactly determines the laws that govern those fields? And why are those laws exactly the way they are? This question takes us to one of the most mysterious frontiers of modern science, the point where physics, cosmology, and philosophy begin to meet. If what I'm saying makes sense to you, and you feel ready to deepen this experience, I've left a more complete material in the pinned comment. You don't need to look at it now. Just remember it when the time feels right. If we accept the idea that the entire universe is composed of quantum fields that permeate all of space, another profound and unavoidable question emerges. If these fields exist everywhere, if every particle is just a vibration within them, and if all interactions in nature arise from these vibrations, then what determines the rules those fields follow? Why do they obey exactly the laws we observe? And perhaps the most intriguing question of all, why does the universe contain this specific set of fields instead of a completely different one? To understand why this question is so important, we need to look more carefully at something we usually take for granted: the laws of physics. Since science began studying nature systematically, one thing has become clear: the universe follows extremely consistent patterns. Gravity works the same way today as it did billions of years ago. The properties of electrons are exactly the same anywhere in the cosmos. Interactions between particles follow very precise mathematical rules. This may seem obvious, but it is actually profoundly surprising. There is no absolute logical necessity forcing the universe to be so orderly. In principle, the laws could be completely different. Gravity could be stronger or weaker. The mass of the electron could have a different value. the strength of nuclear interactions could vary. Small changes in these parameters would make the formation of stars impossible, prevent stable atoms from existing, or even make chemistry, and therefore life, completely impossible. For example, if the strong nuclear force were only slightly weaker, protons and neutrons would not be able to remain bound together inside atomic nuclei. No element beyond hydrogen could exist. On the other hand, if that force were slightly stronger, atomic nuclei would fuse uncontrollably, creating a universe completely different from ours. The very structure of matter would be altered. Something similar happens with the constant that determines the strength of the electromagnetic interaction. This constant governs how electrons interact with atomic nuclei. If its value were slightly different, the electrons might bind to atoms in completely different ways, altering all known chemistry. The molecules that form DNA, proteins, and all biological structures simply could not exist. This apparent precision in the fundamental constants of nature has led some scientists to speak of what is called the fine-tuning of the universe. The idea is that the laws of physics appear to be calibrated in a very specific way that allows complex structures to exist. Not only atoms, but stars, planets, and eventually conscious organisms. But this raises an even deeper mystery. Why do these constants have exactly these values? Modern physics can measure these quantities with great precision, but it still cannot explain why they are what they are. In other words, we know how the universe works, but we still do not know why it works this way. Some physicists believe the answer may lie in an even deeper theory that unifies all the fundamental forces of nature. At present, we know 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of them describes different types of interactions between particles. Electromagnetism governs phenomena such as light, electricity, and magnetism. The strong nuclear force holds protons and neutrons together inside atomic nuclei. The weak nuclear force is involved in certain forms of radioactive decay, and gravity governs the attraction between masses, shaping the formation of planets, stars, and galaxies. During the 20th century, physicists managed to partially unify some of these forces. It was discovered that electromagnetism and the weak nuclear force are actually 2 manifestations of a single, more fundamental interaction called the electro-weak interaction. This unification was experimentally confirmed and represents one of the great triumphs of modern physics. This discovery led many scientists to suspect that perhaps all the forces of nature might be different aspects of a single fundamental structure. At an extremely deep level of reality, there might exist a unified theory capable of explaining all particles, all forces, and all the constants of nature as parts of a single coherent system. One of the most ambitious attempts to achieve such unification is known as string theory. According to this proposal, fundamental particles would not be dimensionless points, but incredibly tiny, vibrating strings. Each mode of vibration of these strings would correspond to a different particle. One specific vibration pattern would produce what we perceive as an electron. Another pattern would produce a quark or a photon. This idea has a fascinating consequence. If all particles are simply different vibrations of the same fundamental entity, then the entire diversity of the universe could arise from a single basic principle. Just as different musical notes can emerge from different vibrations of the same string on an instrument, all the particles in the universe could be different notes, played by the fundamental strings of reality. However, string theory also introduces something even stranger. For its equations to work correctly, the universe could not have only the 3 spatial dimensions that we perceive. It would need many additional dimensions, possibly 10 or even 11 dimensions in total. Most of these dimensions would be compactified at extremely small scales, invisible to our current instruments. This idea may sound like something from a science fiction movie, but mathematically it solves several important problems in theoretical physics. One of these is the attempt to unify gravity with the other fundamental forces, something that has not yet been fully achieved within traditional physics. Even so, string theory has not yet been experimentally confirmed. It remains an extremely elegant, but still speculative hypothesis. Other researchers explore different approaches, searching for new mathematical structures that might reveal the origin of the fundamental laws of nature. While these questions remain open, one thing has become clear over the past decades of research. The universe is far deeper and more mysterious than we imagined at the beginning of modern science. What once seemed like a solid world of separate objects has revealed itself to be a complex network of fields, vibrations, and interactions that permeate all of space. Every particle is just a small excitation in this vast, invisible ocean of quantum fields. Every force is a manifestation of interactions between these fields. And every structure we see around us, from atoms to galaxies, emerges from the continuous dance of these fundamental vibrations. Perhaps the most surprising part of this story is that this same network of fields also gives rise to consciousness. At some point in cosmic evolution, certain structures of matter became complex enough to process information, form memories, and reflect on the universe itself. This means the cosmos has developed within itself the ability to observe and attempt to understand its own nature. And that leads us to an even more intriguing question. If the universe is made of fields and vibrations that permeate everything, and if the human mind is simply an extremely sophisticated arrangement of those same vibrations, then to what extent is our own consciousness connected to the fundamental fabric of reality? This question marks the point where physics, neuroscience, and philosophy begin to intersect. And it is precisely in this territory that some of the boldest ideas in contemporary science are starting to emerge. When we reach this point in the story, something curious happens. For centuries, science tried to explain the universe as a great machine composed of separate parts. Each object would be independent, each event would have a local cause, and everything could be understood by analyzing the smallest components of matter. This mechanistic view worked very well for a long time, enabling the development of classical physics, modern engineering, and much of today's technology. But when we began to investigate the universe at extremely small scales, it became clear that this view was starting to fail. Quantum mechanics revealed a world where the familiar rules no longer behave the way we expect. Particles can exist in superposition, occupying several possibilities at the same time. Systems can also become entangled in such a way that measuring one instantly influences the other, even across enormous distances. Moreover, events that appear random at the microscopic level can produce stable patterns at larger scales. One of the most intriguing phenomena is quantum entanglement. When two particles interact in a certain way, they become part of a single shared system. From that moment on, the state of one particle can no longer be described independently of the other. Even if they are very far apart, measuring one determines the state of the other. This behavior seemed so strange that Albert Einstein famously described it as spooky action at a distance, believing that something in quantum theory must be incomplete. Over time, however, increasingly precise experiments confirmed that entanglement is real. Today, it already serves as the foundation for emerging technologies such as quantum cryptography and quantum computing. But beyond its practical applications, it carries an important philosophical implication. The absolute separation between objects may be only an appearance. At the most fundamental level, systems can be deeply interconnected. This forces us to rethink the idea of physical individuality. If two particles can share a single quantum state, to what extent are they truly separate entities? In quantum physics, identical particles are completely indistinguishable. There is no physical way to label a specific electron and track its individual trajectory the way we might track a billiard ball. For this reason, modern physics often describes particles as excitations of fundamental fields that extend throughout all of space. What we perceive as separate objects may actually be temporary patterns within a much larger continuous structure. This idea can be understood through analogies in nature. A whirlpool in a river may look like a distinct object, but in reality it is only a pattern of movement in the water. If the flow changes, it disappears. The same happens with hurricanes or ocean waves. They have clear shapes and recognizable behavior, yet they are not separate things from the systems that generate them. In a similar way, physics suggests that particles and objects can be seen as organized patterns of energy within universal fields. Atoms form stable patterns. Molecules form more complex patterns. Cells represent higher levels of organization, and living organisms are even more elaborate layers in this hierarchy. This perspective also helps explain how complexity arises in the universe. Even simple physical laws can generate extremely rich behavior when they interact over time. Small local rules can produce surprising global patterns, something we observe not only in physics, but also in chemistry, biology, and even social systems. Life on Earth itself illustrates this idea. In the beginning, the planet contained only simple atoms and molecules interacting through chemistry. Over time, more complex molecules emerged, some capable of storing information and replicating themselves. From there, evolutionary processes produced increasingly sophisticated organisms, eventually leading to nervous systems and brains capable of consciousness. All of this happened without the need for new fundamental laws of physics. The same basic interactions were sufficient to generate an enormous diversity of structures. Complexity, therefore, does not need to be built into the initial rules. It can emerge naturally from the interactions of simple systems. Perhaps the most intriguing aspect is that human consciousness arose within this same process. The brain is composed of billions of neurons connected in networks that constantly exchange electrical and chemical signals. From these networks emerges what we call conscious experience, thoughts, emotions, and perceptions. We still do not know exactly how this process occurs. The relationship between neural activity and subjective experience remains one of the greatest mysteries in science. However, we do know that the neurons and molecules in the brain obey the same physical laws that govern the entire universe. This means that consciousness is not separate from physical reality. It is a phenomenon that emerges within it, a particular configuration of matter capable of generating experience and reflection. This leads to a fascinating idea. If the universe has produced conscious beings capable of observing it, then the cosmos has developed within itself a form of self-awareness. Each conscious mind can be seen as a small window through which the universe observes itself. This conclusion may sound philosophical, but it emerges naturally when we follow the implications of modern physics. If everything is made of the same fundamental fields, there is no absolute separation between us and the rest of the cosmos. We are part of the same process that created stars, planets, and galaxies. And this raises a profound question. To what extent does the very structure of the universe favor the emergence of complexity, life, and consciousness? Are these properties merely rare accidents, or are they natural consequences of the fundamental laws of reality? The search for answers to these questions lies at the heart of some of the deepest investigations in contemporary science. When scientists began to explore these questions more deeply, they realized that the history of the universe can be seen as a sequence of emerging levels of complexity. Shortly after the Big Bang, the cosmos was extremely simple. A hot, dense ocean of energy and fundamental particles constantly interacting. There were no stars, no complex atoms, and no organized structures, only quantum fields vibrating in an intensely energetic environment. As the universe expanded and cooled, the first stable particles appeared. Protons and neutrons began to combine, forming the nuclei of the first atoms. At this early stage, the universe consisted almost entirely of hydrogen and helium spread across vast clouds of gas. Over time, gravity began to act on these clouds. Small fluctuations in density were amplified. Slightly denser regions attracted more matter, becoming even denser. After millions of years, some of these regions collapsed under their own gravity, giving rise to the first stars. Inside those stars, new levels of complexity emerged. The extreme temperatures and pressures allowed nuclear fusion to occur, producing heavier elements. Hydrogen became helium, which then formed carbon, oxygen, and other elements. In this way, materials that did not exist at the beginning of the universe were created inside stellar cores. When massive stars reach the end of their lives, many explode as supernovas. These explosions scatter the heavy elements created in their interiors: iron, carbon, silicon, calcium, and many others, throughout space. The elements that today form planets and living beings were originally forged inside these ancient cosmic furnaces. This means that every atom in your body has an extremely ancient history. The carbon in your cells and the oxygen you breathe were produced inside stars that existed billions of years before the sun. In a very literal sense, we are made of recycled stardust. After these elements were dispersed through space, they began to combine in new ways. Enriched clouds of gas collapsed again, forming new stars and planetary systems. On some of these planets, conditions emerged that allowed complex chemistry to develop. Organic molecules began to form, and some of them acquired the ability to store chemical information and replicate their own structure. This was one of the most important moments in the history of the universe, the emergence of the first systems that we can call life. From that point on, evolution began to operate. Small variations in replicating systems were selected over time. Structures that were more efficient at survival and reproduction became more common. Over billions of years, this process produced an enormous diversity of organisms. Eventually, on a small planet orbiting an ordinary star, a species emerged that was capable of reflecting on all of this. A species that began to question its own origins and the laws that govern the cosmos. This moment marked something extraordinary. For the first time, matter organized into biological structures became capable of investigating the very laws that govern its existence. In a sense, the universe began to study itself through the human mind. When we look at this entire story, we realize that there is no absolute separation between the cosmos and the life that emerged within it. The evolution of stars, the formation of chemical elements, the emergence of planets, and the development of life are all parts of a single continuous process. Each stage depends on the ones that came before. Without the fundamental laws of physics, there would be no stable particles. Without particles, there would be no atoms. Without complex atoms, there would be no chemistry. Without chemistry, there would be no biology. And without billions of years of biological evolution, there would be no consciousness capable of questioning the universe. This shows that human consciousness is not something external to physical reality. It is a natural result of the cosmic process of organizing matter, a phenomenon that emerges from a long chain of events that began at the very start of the universe. This conclusion leads to a deeper reflection. If consciousness arises from the organization of matter, and matter follows specific physical laws, then the universe itself must possess properties that allow complexity, life, and mind to emerge. Some scientists interpret this as a statistical consequence in an immense universe. Others consider the possibility of multiple universes with different physical laws, where only some would be compatible with the existence of life. Regardless of the final explanation, one thing becomes clear. The history of the cosmos is not only the history of particles and forces, but also the story of the emergence of increasingly complex structures capable of storing information, processing energy, and generating consciousness. Perhaps the most remarkable idea is that the same physical laws that govern galaxies are also governing the atoms in your brain at this very moment. Every thought, memory, or question arises from the organized activity of particles that follow the same rules that have shaped the universe since the beginning of time. So when you try to understand the universe itself is using a small part of itself to explore its own nature. The human search for knowledge is not separate from the cosmos. It is a continuation of the universe's own evolution toward deeper levels of understanding. And perhaps this is one of the most extraordinary ideas revealed by modern science. We are not external observers of reality. We are active participants in the cosmic story, part of a process that began billions of years before our birth and that will continue long after our individual existence comes to an end. If this message truly resonated with you, if you felt that quiet inner shift, that sense that your mind is ready for something greater, I left a resource in the pinned comment that goes deeper into this process. I only recommend it for those who feel genuinely ready to accelerate their results, but follow it in your own time. If it calls to you, you'll find it there. If this idea that reality is not made of solid things but of vibrating fields started to change the way you see the world, there is an important step that comes before this understanding. In the previous video, we explored a specific mental state where thoughts stop functioning as ordinary ideas and begin to act more like internal instructions to the subconscious. It is the state where the constant noise of the analytical mind slows down, allowing images, emotions, and intentions to reach the deeper layers of the mind with much less resistance. Without understanding how the mind enters that state, concepts like vibration, perception, and internal alignment can easily remain only intellectual ideas. But when the mind learns to access that deeper level of consciousness, something subtle begins to shift in the way we perceive and interact with reality. The previous video is on your screen now.